Okay, so welcome to the second session of the morning. So we have Bala Sathiapalan from IMSC speaking about aspects of the map from exact renormalization group to the holographic renormalization group. Bala?
Yeah. Thank the organizers for inviting me to give a talk, and congratulations to Bala. Best wishes. So I'm going to talk about some aspects of the map from exact RG to holographic RG. So I'm not actually what I'm going to do is to give a summary of some of the things that we've done and focus on trying to clarify some aspects, one particular aspect of that. And I just realized listening to the previous speaker, Kumar Gupta, that there's some connection between the mathematics of this map and some of the problems that he was mentioning, which I was not aware of, but I realize now. So, okay, so here's the outline of the talk. So I'll talk about, the introduction will be describing, well, the first two parts will be describing what we've done, and I'm going to emphasize the third part, and then say a few things, and then I'll try to say something about the dS-CFT if I can. Very preliminary remarks. So let me begin with the introduction. So what we, as you all know about AdS-CFT, there is a connection between, a duality between a boundary CFT and a bulk gravity theory. And there is something called holographic, so maybe I should just read it, it'll be more systematic. So AdS-CFT conjecture says that the dual to a CFT in d dimensions is a gravity theory in AdS d plus 1. And a famous example of that is n equals 4 Yang-Mills in 4 dimensions, dual to 2B string theory in AdS5. So it arose in string theory, and in string theory, this duality is not very unexpected, because there is a duality between open strings and closed strings, where open string trees are similar to open string loops are similar to closed string trees, and closed strings contain gravity, and open strings are basically Yang-Mills. So as far as I'm concerned, I'm not interested in all aspects of the duality, but the point that I'm interested in is this point, that the radial coordinate of the AdS space in this choice of coordinate is very easy, behaves like a scale for the boundary theory. So here xi are the boundary coordinates, d-dimensional boundary coordinates. Z is the radial coordinate, and you can see that the dxi is divided by z squared. So when z changes, you're changing the scale of the boundary distance element. So it acts like a scale. So if you accept the AdS-CFT conjecture that these two theories are the dual descriptions of each other, then changing Z will correspond to a scale transformation of the boundary theory, which is therefore a renormalization group evolution. So the evolution in the radial evolution in the bulk, which is just it's just that, but because of this boundary connection, it's referred to as holographic RG. Okay, otherwise, it's just a radial evolution. From the boundary point of view, it looks like an RG. This is assuming, so you have to accept this conjecture for this to be true. And what are the things we wanted to, well, one of the things we did, there's a paper with, I should mention the date, this was in 2017 with Hidenori. We showed that starting from an exact RG equations of a CFT, one can derive the holographic RG equations by an explicit mathematical mapping. So if you don't assume this conjecture, and you can ask whether you start with the RG equations of a boundary theory, can you show that it looks like the radial evolution of a field theory in a dS space? And so we were able to do that in a simple example where the fields were fundamental fields, and later in a paper with Pavan Dharni Pragada, who's a student here, and Semanti Datta, who's now a postdoc at ISC. We showed that these techniques apply to conserved vector currents, and it gives a dynamical Maxwell field, and applied to the energy momentum tensor of the boundary theory, it gives dynamical gravity. Okay, so at the linearized level. So this was done at the linearized level, namely the leading equations of motion. For a simpler case of a scalar, the ON model, this is, I didn't say it here, but this is applied to the ON model where you have n scalars, free scalars in the boundary theory. But you can study the ON model at a Wilson-Fisher fixed point, and you can study composites of that and do the same map, and you can get out an interacting bulk theory with where you get a kinetic term plus some cubic terms, and that also agrees with what is known from the conventional AdS-CFT. So indeed, this seems to be a valid method of deriving the holographic RG equations. So I just mentioned, repeat some. So it's interesting because it comes out of RG and does not require the AdS-CFT conjecture in any form, this map. In particular, it does not invoke string theory and seems more general. Because the usual examples of AdS-CFT seem to have come out of string theory where it's to be expected, but here it doesn't seem to be required. Of course, since you have a quantum gravity in the bulk, you might say it's only well defined if you have string theory. So in that sense, string theory does enter, but at least superficially, there doesn't seem to be any requirement of string theory. So this construction of the holographic RG seems to give some insight into why AdS-CFT correspondence exists, and it gives another interesting way to understand gravity. It seems to come out of RG of some field theory which doesn't have RG. Which doesn't have gravity. Okay, so now what I'm going to do is I'm going to summarize the map. So, and then we'll focus on one aspect of it. So the 3 steps. So I should mention that the work that I'm going to talk about is also done in collaboration with the same 2 people, Pavan and Semanti. So this is the map we did with Sonoda. So we wrote down Polchinski's ERG equation for a d-dimensional field theory. That's the first step. The second step is to write down an evolution operator for this equation. And that turns out to be simple because the equation has a simple form. So you can write the evolution operator as a d+1 dimensional field theory functional integral of that. And the extra dimension in that d+1 is, of course, the scale, z, which I've written as e to the power of t. So, of course, already you have a functional integral in d+1 dimensions. So, in that sense, it's already holographic, but it has nothing to do with AdS. Now, this third step, you map this field theory in d+1 dimension to a standard field theory in Euclidean. This is all in Euclidean space because we're talking about a boundary theory which is Euclidean. You can map this to a field theory in AdS d+1. Okay. So these are the 3 steps, and I'll just go over them a little more detail, and then I'm going to concentrate on step 3 for the rest of the talk. So I'm going to say AdS d+1 emerges in the 3rd step, and this step is the main focus of this talk. So I'm not going to say anything new. I'm just going to consider other maps to clarify it, and at that point, I find some of the comments made by Kumar in the previous talk are relevant. Very similar things happen here. So one can ask, are there other possibilities? For instance, in fact, when I first gave this talk at IMSC, I remember the first question someone asked was, can you do this for other spaces? Why AdS? Why not ds? And it seems that you can. So you can make some connection with dS-CFT also. So studying other possibilities also helps us understand better what is going on. Okay, so that's the aim of the talk. So as I said, it's just going to clarify one aspect of this map. There's nothing new. Okay, so the first step is, this is Polchinski's equation. So I just have to define a few terms. So G, I think I've written it here. G is this pointer does, here, that does work. So G is a cutoff propagator. Okay, so it propagates only Well, it's an analytic form, but it basically propagates modes lower than lambda. And psi is just e to the power of, I've written it in this suggestive form, but psi is just e to the power of minus si. I stands for interacting. So this is the interacting part of the Wilson action. So the Wilson action is this. You take out the kinetic term, and what is left is the interacting part. And this equation tells you how the interaction, this Wilson action flows in T, which is this RG scale. So as you increase T, lambda is decreasing, so you're flowing towards the infrared. So T is a flow towards infrared. So this is Polchinski's equation. It's very easy to derive, but I'm not going to do it. And actually, for the purpose of this talk, we'll take D equals 0. So it's just a quantum mechanical system. And I'll, instead of calling it phi of P is the momentum, I'll just call it X. So it looks like a simple Schrodinger equation. So you're just studying quantum mechanics now. And whatever you say, whatever is done here, it can easily generalize to D emission. So it's not a problem. And so of course for this system, P remember was the momentum in the flat directions, the boundary momenta. And here it has no meaning, but it's just written as a parameter. So when you generalize to D dimensions, all these x's will be replaced by phi of P. I think this arrow is not working. Okay. Okay, so here's the solution. So you know, of course, I should mention, how do we go back? Is it possible to go back? This is just Schrodinger's equation without the I. So it's a diffusion equation. So you can use the Feynman path integral as a solution. And here it is. So psi of xi ti is basically your initial Wilson action, parameterized by the xi. This is the evolution operator. So it's a, so the initial thing is a zero-dimensional. So I've put the boundary conditions. X at ti is xi, x at t is x, and then you get the wave function at t. But this is not a wave function. It's a probability. It's like e to the power of minus s I x. So here boundary is a zero-dimensional field theory. The bulk is a one-dimensional field theory with a funny kinetic term, funny because of that g dot p term. And this is holography in its simplest form. But now we're going to change variables to bring the kinetic term to a recognizable form. So this is what we did in our 2017 paper. I'll just repeat what we did. So this is a map. You replace, it's just a simple change of variables here, or a field redefinition. You replace x by f times y, change of variables, and choose your f so that the g dot disappears. So f squared is taken as minus g dot. I've just called it, for the purpose of this talk, I'll just call it an f map. So if I refer to this map, this is what I mean. And if you do that, you get this, what I've written here, where the second term is obtained after the substitution and some and throwing away some boundary terms. You get a term like this. Note this form because this is going to be used again. So it's just the form e to the power of, I've written it in this form, but of course e to the power of log f is just f. It's e to the power of log f, d squared by dt squared, e to the power of minus log f. In higher dimensions, it will be the same thing except with some powers of z in between. Now the whole point is, p is a parameter in this theory. I'm going to choose this to be this, where p is some parameter, m is some parameter, r is some parameter. Okay? And lo and behold, you get a scalar field theory in AdS space. Okay? So this is AdS 0 plus 1. And so here, if you take AdS d plus 1, you will get the corresponding thing in d dimensions. So what does this do? This, now my variables are y, so I get a evolution of e to the power of minus si in terms of y and t, and the functional integral is an integral over an AdS space. Okay? So this is precisely what holographic RG says, as was defined in the original AdS-CFT correspondence. The bulk theory is an AdS theory, and integrating that is supposed to evolve. The boundaries, the field, the boundary action sitting at some point on the at Ti, and as you evolve that T, that's radial evolution, that's supposed to give you RG of the boundary. So here we've started from the RG end and got the radial evolution. And if you generalize, as I said, if you generalize this to D dimensions, you get field theory in AdS D plus 1. Okay? Now, there's some, what is it, before I go on? So before I do that, so this is, as I said, this is for simple, the field on the boundary and the field in the bulk are the same elementary fields. There's some generalization you have to do, which I haven't integrated shown here, when you deal with composite operators. Okay, so when you deal with gravity and Yang-Mills, etc., the boundary or the ON model, the boundary fields are not what are going to occur in the bulk. The composites of the boundary field will be used, and you can introduce a source for the composite, or you can introduce auxiliary fields for the composite. And what occurs in the bulk will be those auxiliary fields. And to do that, you have to write the corresponding Polchinski equation for the composite field action. So that's a somewhat non-trivial step, but I'm not talking about that here. So here we'll just stick with a simple example and proceed with this, where the fields in the boundary are the same as the fields in the bulk, just to illustrate the point. Yeah. Yes. No, it's just a change of variables. P is a parameter. Think of it as a parameter. So the new variable is defined in terms of the old variable. So there's some underlying, there's a P. Yeah. Family of mappings. Yes. X is, see, these are all integration variables. You're going to integrate over X. It's a function. It's a. No, I am taking y is a function of t, x is a function of t. The action will have a p in it. The action, the p enters in the action, because at the end of the day, x is just a variable of integration. You're going to integrate over all x's. Okay, so we would like to understand this map. So I consider the quantum mechanical problem of a free particle with a time-dependent map. So this is where some of the things that Kumar was talking about enter. And so the ERG equation, if you analytically continue it, what did I do? So this, if you take m as minus 1 over g dot, that's the ERG equation. If you analytically continue this to real time, then you just get the Schrodinger equation and the usual path integral with a particle of mass m. And now this mass is a function of t, time. Okay, so now the crucial point is conceptually psi now is an actual wave function. It's not in the Euclidean version, it was a probability. Here it's a wave function. So the interpretation is different, but the two are just an analytical continuation of each other. So we'll do the same thing that I did for that problem, and I'll put x equals fy with f squared taken as 1 over m, and of course you get back the same. Oh, what did I do? Yeah, can you see the red? Yeah. So you get the same combination, and now I'm just going to explore, choose this, instead of choosing it to be z squared, p squared plus m squared, r squared, etc. Just take the simplest example for harmonic oscillator. Okay, take omega squared, and you get a harmonic oscillator. Okay, here there is no time dependence in this. It's all gone, and of course m is constrained because f solves this equation. So your m well, 1 over f has to be of this form, so your m has to be the square of that, cos squared, something like that. Okay? But the point is you get a harmonic oscillator, and this is interesting. And yeah, so this is where the thing that's mentioned by Kumar come out. I found out that I did a search and I found that Padmanabhan has looked, Paddy, he's looked at this problem. This is 2018 actually, not 17. I don't know in what context. He's done the same thing that we did, but his motivation is completely different. He does the same map, and he shows, and he says that the energy of the oscillator is an invariant, and expressed in terms of the original variable, it's this quantity. It's just unintuitive object, but it's just the energy of the oscillator. And he points out that these are just the Ermakov-Lewis invariants that Kumar and all were mentioning. So this method gives a nice way of deriving this, which is different from the method that Kumar gave. I think he mentioned some Russian papers. So I'm not going to use this much. I just want to point out that the same thing is happening in the AdS case also. It's just a different map. Of course, now you can explore and try other maps. But now you can do the analytical continuation of this with the free particle Schrodinger equation and do the same thing. And actually, you can try to do this at the level of the equation. So previously, I was doing it for an action and the path integral. Now you can do it at the level of the equation. And the way to think about it is these are, you should think of these as canonical transformations. Anything that preserves the commutator is defined as a canonical transformation. So you can show that if you do this, if you define your wave function, a new wave function like this, with some alpha which is defined to be that, then this equation, and you choose the same f that I did before, the action, you will get the Schrodinger equation for harmonic oscillator. And there's a constant due to some ordering issues that comes out, but this constant doesn't depend on y. It just scales the wave function by a fixed amount, so it doesn't really have much importance. So you get the same equation, the same method. So that's another way to understand this map. What you're doing is some kind of a quantum mechanical canonical transformation. This is also interesting. There are some papers by people studying in the context of AdS-CFT trying to map the RG equation to the bulk, and they find that their kinetic term has non-local terms and they use canonical transformations to get rid of the non-locality. So this seems to be doing that, getting rid of all the non-locality immediately, because the G of P is in some sense infinite number of derivatives, so it's a non-local thing. So this is getting rid of that. So that's another way to think of it. Okay, so analytical continuation. So now if you analytically continue the Schrodinger equation, you get the ERG equation. The ERG means exact RG equation. And so you can do the same thing for the harmonic oscillator. Choose this, and you will get the Euclidean harmonic oscillator. So you can start with the Schrodinger equation and do this map, and you'll get a Euclidean, you'll get a equation for the wave function. If you do for the Euclidean case, then you get an equation for the Euclidean version of the wave function, which is the probability, which is e to the power of minus s. And these kind of conditions remain the same. So now you can, okay, so here's a summary. The Euclidean free particle ERG equation can be mapped to a Euclidean harmonic oscillator if you choose this, and the Euclidean AdS theory if you choose the second one. So this is, of course, I've done all this in 0 dimensions, but you can do this in d dimensions, as mentioned. Now you can analytically continue the ERG equation to get a free particle Schrodinger equation, but you could equally well analytically continue, wait, I haven't done that. The quantum mechanical free particle Schrodinger equation can be mapped to a harmonic oscillator if you choose this. So now the question is, can you, instead of omega squared, if I choose z squared, p squared plus z squared, r squared, is there an analytical continuation of that? And the answer is yes. Answer is again, that's a well-known thing. You get ds. The analytical continuation you do is I eta, you call z as I eta, r as IL. Choose the same map that we did before, this map, and you get the quantum mechanical evolution for a wave function in de Sitter. But I emphasize that now we're doing quantum mechanics, it's not statistical mechanics, so psi is an actual wave function. Previously, psi was just e to the power of minus s. Here it's an actual wave function. So that's basically, now I'm just going to summarize the conclusion and that's the end of the talk. So this map can be understood as canonical transformations in the quantum mechanical problem. So you can map the free particle with prescribed time-dependent mass to a harmonic oscillator. In the Euclidean case, psi refers to a probability of the form e to the power of minus s. In the Lorentzian case, it is a quantum mechanical wave function. The ERG equation maps to a holographic RG equation for psi. You could equally well analytically continue the Schrodinger equation, and it maps to a quantum mechanical evolution equation for psi, which is of that form. And this can be generalized to d dimensions. So there are two things you're doing. There's a map and there's an analytical continuation. And you can do the map first and then analytically continue, or you can first do the analytical continuation and then do the map. And either way, you'll get the same thing. So you could start with the ERG equation and analytically continue to a free particle Schrodinger equation, which maps to quantum mechanical evolution in de Sitter space. Okay? Or you can start with the ERG equation, map it to holographic RG, which is this map of change of variables, and then analytically continue to, and then you get Euclidean AdS, which can be analytically continued to quantum mechanical evolution in de Sitter spacetime. So at the end of the day, this gives us the statement of the dS-CFT conjecture, which has been made before. And the statement is this is a last slide. Psi, the wave function of de Sitter, is related to, so the left-hand side is a wave function. So the left-hand side refers to a d-dimensional spatial slice of a d plus 1 dimensional quantum mechanical theory. And you're getting a wave function on that. The right-hand side is actually something like e to the power of minus the Wilson action, which is like a partition function, but analytically continued. So this is a particular partition function or a generating function of a CFT, and you analytically continue it. So this is the way, and so in this sense, to the extent that RG can be mapped to holographic RG in Euclidean AdS, you can map RG to de Sitter wave function also exactly the same way, with an intermediate step of analytical continuation. So that's basically what I had to say. So I've left out all the complications of dealing with composite operators, etc. But at the simplest level, this is all there is to it. Of course, now you can go ahead and start talking about what you're going to do with this wave function, how you calculate expectation values, etc. This is done in some papers, and they point out that calculating expectation values with this object in a quantum mechanical theory gives different results from the analytical continuation of this, because when you calculate an expectation value of the wave function, you have to take psi star psi. So you don't just use psi because it's a wave function, not a probability. Okay, but those are all, there's nothing new in all that. So I think I'll stop here and
Any questions on this? Yeah.
Some non-locality and like by some change of variable,
yeah.
get locality. So I'm confused, like locality is supposed to be some like physical property, right? Like how can by change of variable you can?
No, it's not. The point is, it's not the different. It's not really a non-local theory. The non-localities of the form when you cut off a field theory, the non-locality emerges because you're integrating out modes. And so it's not an unphysical non-locality. It's a physical, your bare theory is local even in the CFT. It's because you've integrated out some modes that it looks non-local. But we're saying we can map that to a problem which remains local all along. That's all. So your starting theory is local, it remains local. But the price you pay is that the action depends on the coordinate z, but it depends in such a nice way that it looks like an AdS space.
And I mean, in this whole analysis, this particular property of the metric is very important. Like this.
The AdS metric.
Huh.
Yes, the AdS metric has this nice form that the z tracks the scaling. The z dependence tracks the scaling, which is what you want in an RG also. The in a dimension, when you write in terms of dimensionless parameters, say near a fixed point, you don't have dimensionless parameters, so all dimensions are made up with powers of lambda, and that becomes 1 over z, and so all those powers of lambda become powers of z, and that's exactly what is required in an AdS metric.
So if I have started with some other metric in the AdS, it would not be that much visible. Right?
Oh, you mean other choice of metric? Yeah, it would be not so. It would not be so obvious as in this metric, but I think the results will be the same. Yeah.
Let me say, this is my ignorance.
Okay.
It seems to me that AdS is ruled out experimentally. Okay? That's what I hear.
AdS.
So why? And it is also for cosmic scales, and this is, I suppose, for microscopic physics. So I don't understand the relevance of this correspondence at all. Okay? If it is for microscopic physics, where does AdS come from? A convenience. And you said ds.
Yeah.
ds has the orbits are accelerating particles in the Rindler wedge.
Yes. Yes.
And the operator which does the evolution is the boost operator. But the boost operator is unbounded below. So the energy is unbounded below. Again, I don't understand the physics. I mean, you can do mathematical calculation. But what is the physics of this, I don't understand. Also, cosmic scales, there are all kinds of things.
No, you have a wave function evolving it quantum mechanically, that's all.
So the energy, the expectation value of the energy will be unbounded below. So I don't understand.
But we are living in a de Sitter space.
Huh?
We live in a de Sitter space.
De Sitter space, it will be unbounded below, yes.
Oh, whatever it is, that's the real world, no?
Unbounded below.
We are in a de Sitter space. There is a cosmological
That is
concept.
in large. I don't know that that de Sitter space is relevant for microscopic physics.
Oh, okay. No.
That I don't know, okay? Because there are so many things happening.
No, actually, yeah. So I'm not addressing any of those questions. All I'm doing is making the connection between the dS-CFT correspondence that people have made in the literature, the AdS-CFT correspondence that people have made in the literature, and how it all ties up together in a mathematical form.
But what is its physical relevance?
Of AdS-CFT?
This whole approach.
It's
is very
physical
popular.
relevance is just that you have a field CFT, and it has a dual description which allows you, which is a useful description. That's all. But it's also a way of understanding. It's also a way of understanding how dynamical gravity can come. Imagine the AdS scale is very large, so it's very close to flat space. So you have a dynamical gravity coming out of as dual to a theory that is no. Yeah, okay. I mean, I have nothing more to say than what anyone else has to say.
So Bala, when you went to the dS-CFT,
Yes,
so which do you get CFT at Scri plus or Scri minus, or it doesn't? It depends
So
on how
here
you get
we're using those coordinates where at t equals minus infinity it's a light-like thing, and t equals plus infinity is space-like.
So you get Poincare patch.
Yeah.
So when you do
it's a
the
Poincare
full,
patch. It's a Poincare patch. Yes.
So when you full RG evolution, you go from the one of the boundary to the horizon.
Yes, correct. Or from the horizon to the boundary, whichever way you want to do it. Yeah.
So, Paul, let me just add a few words about the physical relevance of the AdS-CFT correspondence. So dS-CFT, I think, is very interesting. I'm not sure I know how to answer the question, but it's interesting since we live in de Sitter space, but I put that aside. So you can try to use AdS-CFT in two ways. One is to learn about quantum gravity, which maybe others can speak more about, or it's to learn about the gauge theory side. And so in terms of thinking about how does it relate to the real world, you can either try to relate it to the quantum gravity of the real world, which is what many people have done, or you can think of the CFT as a model for QCD. In particular, if you go to finite temperature, n equals 4 superioring mils at strong coupling and finite temperature is a nice toy model for quark gluon plasma at high temperatures. And the big advantage of AdS-CFT is that strong coupling in the gauge theory gives you classical general relativity on the AdS side. So impossible questions like equilibration, strong coupling dynamics, viscosity, transport coefficients, things that are very, very hard to calculate in quantum field theory become easy calculations in gravity. So anyway, just to say that there are ways of relating what Sathiapalan has talked about to the real world, either by trying to think of the real world as the gravity side or by trying to think of the real world as the gauge theory side.
We can move on to Justin.